Hi, good morning and good evening to different time zone participants. Glad to be part of the speaker for today's conference. I'm Sui Heng from Intel Malaysia Logistics, partner with Alan Creed from Intel India Supply Chain Innovative Lab, and Nor from Ormi Technical Support. We will share with you our success warehouse simulation project using AnyLogic through our strong collaboration between Malaysia and India two sides. As per the title of this slide that you can see, we use AnyLogic to build ACR model in warehouse environment. Next slide, please. Let me run through the agenda that we will cover today. I will walk through the project background and objective. Nor will brief the technical part of AnyLogic model, logic, 3D, and diagnostic outcome. Last but not least, Alan Creed will share a what-if scenario and how we use AnyLogic software to simulate the predict outcome. Next slide, please, Alan Creed. Okay, now let me do a quick background introduction. ACR on bullet number 3 stand for Autonomous Case Handling Robots is one of Intel warehouse digitization project, and it is piloted at Chengdu warehouse site. Full implementation has go live starting last year December, which means Chengdu warehouse has been running this ACR system about 9 months duration. And as part of digital twin efforts, we picked this project to use a simulation tool to study the robot's productivity, perform what-if analysis, and also determine the robot's utilization to maximize the system capability. This ACR system consists of 4 big robots and 8 small robots to execute the inventory, totes, pick, and place without any human interference within the floor layout. Next slide. We will play a short 1-minute video to show the actual Chengdu site's ACR robot pick and place process. You can start, Alan Creed. Yeah, so now you can see the operator perform the inbound and outbound inventory transaction through a PC. They will do the scanning. So for inventory tote placement, you will see a small robot moving to the operator part, and then they will pick the tote to place on the buffer station. Then they will move to the bottom buffer rack. Once the big robot receives the signal, and it will come to pick the tote from the bottom buffer rack to the respective upper rack storage location. Now for picking process, once the big robot receives the order from operator from front PC, it will move to the desired storage rack to search the totes and then place the totes on the bottom buffer rack. Then small robot will then pick the buffer rack totes and send to the buffer location for operator next steps, which is the unit splitting or packing process. Next slide. There are 4 objectives of using AnyLogic. Firstly, we want to simulate the ACR system with a 3D model robot movement logic at warehouse. Secondly, we use AnyLogic to ingest actual inventory data or generate the order data within a specific duration. Third, we also aim to obtain the KPI includes robots utilization percentage and shiftly productivity, also known as the run rate. Lastly, we create a what-if scenario to get AnyLogic analyze the potential productivity. Okay, next slide. I will pass the mic to Nor, who will brief more technical details how we create the model until the diagnostic outcome. And for your information, it takes us about 6 months duration to complete this simulation project from starting data gathering, logic building, debugging, and design the diagnostic page. Nor you can continue for next slide onwards. Thank you.
Thank you, Sui. Hi, this is Noor. So I will walk you through the 4 stages in which the simulation model was built. In the first stage, a physical model, that is something we can see, touch, and interact, was recreated with the highest accuracy as possible. Once these physical objects were established, in second stage, can you please go to the next slide? In second stage, implement the logic defining the interaction between these objects. These included interactions such as determining storage locations for the incoming inventory, assigning robots to move the inventory between the storage location and the work centers, routing the robots through different picking and placing resolution, and resolving the collisions. The collisions included rear end collisions and the head-on collisions. In this stage also involved developing what is referred to as configurations, which are combination of physical objects and their associated logic. An example of configuration would be determining which storage location to assign a piece of incoming inventory. For instance, assigning a location near a work center to reduce the effort on a small robot is one configuration, while assigning a location close to an idle big ACR is another configuration. Next slide, please. So here we are showing a video which includes the parts of the solution which we developed. So this is the model. This has all the physical objects, that is the storage, the paths on which the robots move, the actual small and big robots. In this part of the video, we are looking at the logic which define the interaction between these physical objects. And in the third stage, in this part of the video, we have a 3D animation of the model, which was used to verify whether the model is built as per our stated requirements. In the third stage, a diagnostic tab was designed and developed to measure the performance of the configuration based on some KPIs important to the business. So in this part of the video, a part of the solution which was to exactly replicate the Yes. So in this part of the video, what we are showing is a part of the solution which was to exactly replicate the moments of a big ACR. The next part of the video shows one of the features of the simulation model, that is to detect the collision and to resolve this collision. So here the less priority robot goes to an idle location and gives the way to a robot which has the task of the higher priority. Next slide, please. In the fourth and the final stage, once the diagnostic tab was built, experiments were conducted on different configurations of the model. So the details of the diagnostics tab and how the experiments were conducted will be explained to you by Alankit.
Yeah, thanks, Noor. Good morning and good evening, everyone. So Suhen give you the background of the problem statement, what we were trying to do. Noor explained how we developed the model, and I'll be sharing the diagnostics part of it. So in the diagnostics tab, we wanted to see what is in the current configuration, what is the total productivity that we are able to achieve. So here we had a tab which shows, okay, how many boxes were being picked and placed in a day. Here is for the picking, the R-wise split during the day. Similarly for placement. Here we have, these are the different product types that we have, and this is the current inventory status of each of these products throughout the day. And then our most important parameter was robot utilization, both the big robot and the small robot utilization. So we wanted to be able to measure how much the robots are currently being utilized. And from this analysis, you can see like the big robots are more than 90% utilized. So it might make sense that we get another big robot, because if one of the robots gets a breakdown, right, then the entire warehouse operation can get impacted. It looks to be the bottleneck in the operations. Similarly, if we see the small robot utilizations, all the small robots are, almost less than 50% utilized. So it might suggest that, okay, we might have a few more small robots than we would ideally require. But yeah, because the small robots are less expensive and more flexible, so I think it's fine. And so for the diagnostic high level, these are the things that we are trying to measure. Then we also did a stress test to see how much maximum load our system can happen. In the previous diagnostic tab that I showed, we took the actual inventory data and then we ran it through the simulation model to tell us how much the robot utilization we are getting in the current order, the current loading we are giving to the system. Here, we have also written a Python script which can simulate order data and then run it through the model to see how much maximum productivity we could get. So we were trying to see if we run, or if we only do placement, how much maximum productivity we can get for the placement. Similarly, if we only do picking, how much we can get, and what is the robot utilization that we are able to achieve in that way. So that is what we're doing here in the stress test analysis. Another important thing that we tried to do was a what if scenario analysis. Right now, what happens is whenever an order is there, so suppose there is an order for picking up boxes. So first big robot needs to pick the particular tote, right, and transfer it. So right now, in the current logic, in the current implementation, there is no prioritization given between outer totes and inner totes. So sometimes big tote might be assigned a tote which is at outer layer. Sometimes it might be assigned at an inner layer. But what happens is if we have to pick an outer tote, the big robot can directly get it. But if it has to pick an inner tote, first it has to take out the outer tote, move it to one of the shelf here and the big robot. Then it has to bring the inner tote, bring the inner, first it has to take the inner tote, bring it above. Then it needs to take an outer tote. Then again, it needs to put back the inner tote back to its location, right? So there are a lot of additional steps that it needs to do if it is supposed to pick an inner tote. So in this what if scenario analysis, we implemented a logic in the robot to prioritize outer totes. For example, if a product is available both in outer location as well as inner location, prioritize the outer tote location, and only if that product is not available at outer tote, then only assign it to the inner tote. And we wanted to see that if we were to do this implementation in the actual logic of the robot, how much more productivity will we be able to achieve? This is the result of that test. So on the left, we see all layers where the robot, there is no prioritization and the robot can pick randomly between an outer tote and an inner tote. So if you see this is the robot utilization, around 88% robot was being utilized. And this is if we prioritize an outer layer picking, and only in the event when outer layer is not available for that product, then only go for inner layer. And the numbers are hidden here due to data confidentiality. But picking, we were able to do 15% more picking and 40% more placement in only the outer layer when we prioritize that. And one more interesting thing to see here is we were able to do more picking and placement operation, but the robot utilization was actually a bit less than compared to if we were only doing all layers. And the reason for this is because if we were to do both the layers, then like we showed here, there are a lot of unnecessary steps which keep the robot utilized. So by implementing this, one is we are able to solve our problem of what we saw in the earlier, that our big robots are being overutilized. By implementing just the outer layer, one is we are able to get more productivity. Another thing is we are able to also improve our robot utilization as well, because more work they are able to do and even with less utilization. So this was a really important result that we were able to demonstrate using the simulation model, that we are able to more efficiently utilize our robots and also have over 30% more increase in the productivity. So yeah, this is something that right now we have proposed to the robot team from the vendor from which we have procured the robot, to try to implement this logic and see what are the actual improvements in productivity that we are able to get. So now summarizing the benefits of using AnyLogic and this simulation study. So we are able to ingest actual data so that it becomes sort of a digital twin where we can put actual data and then see what are the productivity numbers that we can achieve. And also we are able to load simulated data to the model to do some sort of stress testing to make sure that we are able to properly load the warehouse. Another thing is we are able to measure the robot utilization to assess if we need more of few robots or if we have excess, if we have shortage of some robots, if we have excess or shortage. Another thing is, like I mentioned, to measure productivity, to optimally load the warehouse. And then we were able to do this what if analysis, which suggests that if we prioritize the outer toes picking and placement, then we can have increased productivity. Now, as a next step of our simulations study on the model results, what we are doing right now are we are implementing these results on the Chengdu ground. So they are implementing and validating these results. Another thing that we can now do is we have now configured this for a Chengdu layout, but we can easily extend this model to any other new warehouse layout configuration. Because for Chengdu, like first we had procured and now we are doing the simulation, but now because we have the model, first we can run the simulation model and then suggest how many productivity we'll be able to achieve and how many robots are actually required to be procured in that particular warehouse. And finally, another thing that we want to do is right now we have just replicated the order logic and prioritization which is built in the robot, but we also want to build our own algorithm like order assignment and robot routing algorithms to see if there is any scope of further optimization or improvement. Yeah, that's about a presentation. I would like to thank you everyone for attending. And yeah, we are open now for any questions that you might have. I think there's some. Yeah, hello. Okay, I think we have 4 questions. I can't hear you. Hello, Noor, are you talking?
Yes, we do have questions in the
Can you hear me?
Q&A box. Yes, I can hear you.
Okay, I think the first is, can you tell me, Ryan, what are the unanswered questions? Okay, these are the open ones. How was the model validated with real warehouse before conducting what if analysis? Okay, actually the thing is, first we have conducted this what if analysis in the model, and then we are sharing these results with the warehouse team. So they are now validating if actually they are able to run this. So during the downtime, like we have an operation shift in the warehouse. So during that time, we are trying to see if our model results are consistent with what is actually if we are able to improve the productivity or not. Another question, Noor, I think is related to the collision avoidance. If you can answer that, how was it implemented?
Yes, so what you say here, the collision avoidance was implemented using the shapes for shapes like the rectangular for the ACR, and then have a probe if it enters another ACR's that rectangular shape area, there is a collision. So yes, the precision might take a hit here, as you have discussed, but the robots are big enough here. They are in in the measurements of, I think, meters. So we did not much focus on the precision here. So we use the shapes to make this collision detection algorithm.
Yeah, thanks, Noor. I think another question is the timeline from which we moved from ideation to actual implementation. And I think, yeah, Sweng already mentioned it took us about 6 months when we started the engagement, then understanding in detail the, logic and movement of the robots step by step, and then conversion into the final, like initial model, then first Noor build, then we iterated over it to make sure that it matches the actual warehouse logic that is implemented in the robot. So yeah, around 6 months of time it took us. Is there any other question? This is a kind of OR problem where you are optimizing resources and reducing process downtime. Does rack configuration or layout and robot energy levels or battery power taken into consideration in your model? Swing, can you answer this one maybe?
Which question? I'm looking at the question.
Asked by Rishabh Tripathi.
From which name?
Rishabh Tripathi. Like our robot energy level or battery power, why we didn't consider them in our model?
Reduces process. Does rack configuration or layout or robot energy level, battery power taken into? Also, for this case, all the maintenance and battery charging area is excluded from this model. We only focus on the robot, the big robot and small robot picking and placement time. So wherever our data, information loaded in AnyLogic is based on, our scope is on the robots pick and place time study.
No, this is not an academic related project. This is an actual project in Intel warehouse as part of our digitization initiative. I think
did you answer the Rishabh Tripathi's question? This is a kind of OR problem where you're optimizing.
No, not it.
Yeah, so this is not an optimization problem. So what I said that there are different configurations which we want to experiment with. So instead of experimenting with physically, we designed a simulation model where we put in the configuration and put some load on the system and see how that configuration is working. Whether it is providing the necessary output that we are looking for, or do we have to make any changes? This is a kind of OR problem. This is a kind of OR problem where you are optimizing resources and reducing process downtime. Does rack configuration? So we are not optimizing here. Actually, we don't know whether whether any particular configuration is good or bad. It's only when we run the simulation we'll get to know what is the output. So we are not optimizing it here. We are checking how the particular configuration is working.
Another question, Noor, is like, how did we make sure that we replicated the system correctly?
Where is the question?
I think they put it in chat instead of the Q&A.
Okay. Let me check. Can you repeat the question again?
How did we make sure that we have replicated the system correctly?
Yes. So for the physical layout, we have the CAD of the shop floor. And for the robots, we actually have the dimensions of the robots and also the characteristics of how the platform moves, what is the speed of the platform. If it has to pick up from the back side of the rack, what is the speed? If it has to be picked from the front of the rack, what is the speed? So as I said that we have tried to make the physical objects as accurate as possible, but at the end, all the data that we can gather and put also has its limitation. The tool also has its limitation, but we have tried to make it as accurate as possible to the actual physical layout.
Yeah. Another question is, what was our biggest challenge during the AnyLogic implementation?
Maybe this one I can help. We did struggle a lot during this 6-month duration. Firstly is the data part. Remember during when we gather the data from the machine, the supplier data file, and there's 1,000 tons of data. We need to massage the data and then we pick what is the actual data we needed to load into AnyLogic. So we have to decide which is the necessary data and which is the not necessary. And from the raw data, actually we have multiple product inventory, but due to the times control, right, we fixed to select 5 inventory only. 5 type of the product. Then our second challenge is on the logic build. which is we need to further understand on the process, how the robot running across the ACR system and interact with the small robot. Because we collaborate with different sites, people, like Malaysia side, Chengdu side, and also India side. And not everybody stay in the actual production or warehouse, look at the actual process. So we also go through a lot of video or camera system showing the actual process in the warehouse, and then we determine how the process and our boundary scope. So at the end, we decide to start from the picking and placement process only. So we exclude those like operation processing time or the lot scanning time.
Yeah, thanks.
And
Another thing is because the big robots, what you see in the model, right? They're not an agent already available in the AnyLogic library, right? So yeah, Noor had to build a custom agent with the animation, etc., to enable that.